which means not like other channels in which you will just discuss only the most optimal approach. Nah, we will discuss the most important problem which you might face, that why it is not a DP problem. Because for sure, for the people who have been doing DP for so long, they will for sure think of in the very beginning it's a DP problem. But again, no worries whatsoever, we will think of everything from very scratch, and again there will be many ways which we will be discussing in this video. So let's start off. So the problem is furthest building you can reach. Now it just simply says that we are given an integer array called as heights, and we have like all the buildings are basically height says this building has this specific height. Now some bricks and some ladders are given to us. Bricks as in, you know, bricks, and ladders as in, okay, it can reach any height. I'll tell you more on if you don't understand what this ladder and bricks will do. But you can start your journey from the building 0. So the initial building, the very leftmost building is the building 0. And then I can move on to the next building by possibly using bricks or ladders. Now how I can use those bricks or ladders? I can simply say, if I am at the building I want to reach to my next building, which is I plus 1, then I'll just simply check if I am at a higher or an equal building, which means I am here, which means I, and this is I plus 1. So I am at an equal building. Oh, no ladder or brick required. See, ladder or brick is required when you have to do a higher jump. You have to do a higher jump. So you will put bricks on this ith building, and then you will be able to jump to the I plus 1th building. Or let's say if it is very large, then you will put a ladder from I to I plus 1th building. That's it, right? If it is equal or if it is less, then you don't need a ladder or a brick. You can simply jump, directly jump, because you are Salman Khan. Not Salman Khan, but Hrithik Roshan. Cool. Now, or maybe John Wick. Cool. So what you can do is that, okay, if the buildings are same or equal, then you don't need to jump. Now, but if the building is actually high, which means I am at the ith building and I have to go to I plus 1th building, then the jump is high. So I have to use either a ladder or a brick. Now how they are used is, let's say the height difference, let's say the height right now of the smaller building is 4. The height of the larger building is, let's say, 9. So I would need, and I know the height difference between them is 5. So just imagine that a building is made up of one brick. It is made up of one brick. So I can say this 9 height is made up of 9 bricks. This 4 height is made up of 4 bricks. So if I have to jump a length of 5, I would need 5 bricks. But I can say I can also use a ladder directly. One ladder can do as high jump as possible. Whatsoever jump is possible can be done with a ladder. So now your question is that you will start off from the index 0, and then you have to know what is the farthest building index. Again, I'm not saying the farthest number of buildings you can reach. I'm saying give me the farthest index of the building you can reach from the index 0. And that's your question. So first very obvious thing which should have or could have come to your mind, again, it entirely depends upon how optimal you start thinking, but in an interview you should for sure go about greedily, like go about brute force approach. So the first thing which can come to mind is, okay, if Aryan I am at the ith index, then I would know that, okay, I am at the ith index and I have to jump on to my I plus 1th index. That is the option which I have, right? And I have in that jump, in that I to I plus 1, I have 2 options. Either I can use a ladder or I can use a bricks. Oh, I'm doing an operation. I have 2 options. Doesn't it sound like a DP problem? Oh, I am at the ith index. Again, for many of you, it might not sound, but for the folks, again, there are many folks who have this problem. That's the reason I'm discussing this. It wastes time, I know, but still, if you know that, you can skip this part. Now, for sure, it is ladder and bricks. You have 2 options, then you can jump onto these. So it seems like, okay, I have 2 options, and for sure, if I try for all the possible 2 options for that specific index, it might end up doing a recursion, but I can for sure memorize it, because we have seen similar kind of problems in which we can memorize if we have 2 or more options. So like I can say option 1, option 2, option 3. Now, like, it's not like that, okay, ladder or a brick. If I am at the ith index, I have to jump onto I plus 1. I can simply say, if the I plus 1 height is itself low, okay, if the height of I plus 1, if it is equal or less than height of I, then I don't need any ladder or brick. So my ladder or brick will remain same. I can simply go and jump onto I+1 with increased number of index. My index has increased. But if it is not the case, then I have to use either a ladder or a brick. So choose and try to see which one will give you the maximum answer, which means maximum distance. So I simply say the height difference from I to I+1 will be h of I+1 minus h of I. So now, and I know that if I am using bricks, so I have to use, for height difference, I have to use the bricks. So I can simply say that bricks minus height difference should be more than equal to 0. Then I can use those many number of height difference bricks. So I can simply say that bricks minus height difference will be the remaining number of bricks, because all those height difference, whatsoever was the height difference, that many number of bricks I have used right now. Cool. And for sure I did not use ladder, so ladder will remain as it is. And then I can move on to I+1. So you can see, okay, I moved on to next index. But Aryan, what if my ladder is more than 0? Yeah, for sure. You should try on when your ladder is more than 0. You can try on to use the ladder and see if maybe using a ladder is optimal solution. So I will use a ladder here itself. So you will see your DP state, you have your I, which is being changed, you have your bricks, which is being changed, you have a ladder, which is being changed. So it is kind of, your DP state would have I, bricks and ladders, which is, and you will try to maximize the index which you can reach ultimately. Base case and stuff, I will not discuss it, because it is, you can for sure see I, bricks and ladders. I is 1 is 5, bricks is 1 is 9, ladder is 1 is 6. So it will be very high complexity. Now, you know, you can apply DP, but this will give you a TLE. Although you might say it will also give you a MLE, but to optimize your MLE problem, you can again, that's a maybe, you can maybe use and concatenate that as a form of a string, which means usually when we get MLE in this kind of stuff, we use a string as a hash, which means rather than making a DP as a vector of vector of vector, I'll make as an unordered map of integer and the key and the value, and the key will be nothing but a hash, which means I hash brick hash ladder. It will be a string, and that I can use as a key to memorize that, but still it can also give me MLE. So now we know that we can apply DP, but it will give us TLE. It's the reason that people will not discuss the DP approach in this problem, but still you should be knowing, because you should be knowing this approach, because there is exactly similar problem, which is minimum number of refueling steps. This also uses the exact same approach, which means the most basic approach which you can go about as a starting approach in this will be a DP approach, which will be O of n square in this case, because you can read the problem after this problem, but yeah, you can try this problem for sure. It is exactly the same, and the same way we will optimize that with using the same approach. I'll not discuss this right now because I want to tell you the intuition behind it. So now we know that, okay, we cannot apply DP. We have to do something else. Now, what can be something else? See, by the fact that you can use only ladder or a brick, you would have known the difference between them. Ladder for sure. Ladder can be used for a very high difference heights, which means I is here and I+1 is here. Then you will for sure use a ladder, because it's a very high difference. If you will use this many number of bricks, you will actually be exhausted. For example, if you had a height here, and then a height here, and then a height here, and then a height here. Let's say you had one ladder and some bricks. So from here to here, to jump, if you use one ladder, then from here to here and from here to here, you will have to only use bricks. And you can see there are many bricks required, which I might not have. So isn't it optimal that for very large heights, I will use ladder, for smaller heights, I will use bricks. And that's most greedy approach which I should take, right? So that's the reason I will just think of, okay, for larger jumps, which means for larger height jumps, again, remember these heights are increasing jumps, which means as in from I to I+1, I am jumping in a more height. So in that specific jump, if the jump is very large, I will try to use a ladder. If the jump is small, then I will try to use a brick. That is the most optimal, most greedy approach which I can think of, and that seems completely fine to me, because it is very optimal that in the very high jumps, I should try to take a ladder rather than my bricks, because maybe bricks I can use it for smaller jumps, maybe in future or maybe before also. So now let's take this example itself, which was the example 2 of our problem, and from this itself we can just try to see how we can do it. Now again, every time whatsoever we will go on and try at the ith index. Okay, let's say I am at this index. Now I have to just figure out if I can reach this ith index or not in this, because ultimately my aim was to reach the maximum index, but right now I am saying let's try for the ith index, and I will apply the same greedy funda which I thought of above, that whatsoever height differences I have, maximum height differences, which means maximum height which I have to travel, actually I will use ladder for that, and for the minimum ones I will try to use bricks. So if I am at this specific ith index, and again I know I have to start from the building 0. So here to here I will have to jump 8. Again, 8 is nothing but 8 bricks distance, but I can say 8. All are same. Okay, from 2 to, again from here to here, no cost required. Right, from 2 to 3 I will have a cost of 5. Okay, and from 4 to 5 I have a cost of 15. So I know that to reach up till the ith index, I will have to require a jump of 8, a jump of 5, and a jump of 15. So this is what I require, but I already saw that I will use greedy approach. In that greedy, I will just say, bro, I know I have 2 ladders. So maximum heights whatsoever, maximum 2 heights whatsoever you have, you can use ladder for that. And for the remaining heights, just use the bricks. So I know that, okay, I will just simply sort it down because I want maximum k values in the end. So I can simply sort it down. Okay, I simply sorted it down. I will choose the maximum 2 jumps, and that can be performed because of ladder. The remaining ones, which means these maximum 2 are gone. It can be performed by my ladder. The remaining ones, jump whatsoever is remaining, that should be performed because of my bricks. So I know the remaining jumps are, although in this case the remaining jumps were just 5. But still, if I had multiple also, let's say 5, 2, and let's say 3, then I would have to add these jumps because I want to do all of these jumps to reach my ith index, right? And that to reach my ith index, I will just do a summation of all these jumps required, and that should be less than or equal to my number of bricks which I have in my input. And input I have 10 bricks. Right now in this case, I required only 5 bricks. So I use those 5 bricks, and yeah, for sure 10 is more than 5. So I can for sure utilize my 5 bricks, and still I would be remaining with my 5 bricks, which not useful for me, but maybe. So with this fact, you can easily see that I was able to reach my ith building, and that too, I was at the ith building, and then I figured out, will I be able to reach this ith building? For that, I just simply went back and saw how many, what all jump lengths are required in that maximum k jump lengths. Again, k is the number of jumps, my k is the number of ladders which I have given. So those many number of jumps I will give to my ladder, because he can perform it as soon, anyhow. The remaining jumps I will do a summation, and that should be less than or equal to my bricks which I have given. So for sure, you can simply see that this operation, again, I want the maximum building. So this operation I will perform at every building. Okay, right. Initially, I will go at the first building and see, just gather the information before and see if it is possible or not. Then go on to my next building, see, gather the information. Again, when I say gather the information of the jumps required. Then I'll go on to my next building and again check. I'll keep on checking. There will be one point where it will say, bro, it is not possible. And for sure, if it is not possible at this index, so this is the farthest index which I could have reached. So you can simply see that you go on to all the indexes, let's say the ith index right here, and for this specific index, I will get all the previous jumps. Those jumps when I have got with me, which means, okay, all the previous jumps lengths I've got with me, I have to sort all those previous jumps. And after that sorting, I have to grab out k maximum jumps from that, because ladder can perform those k maximum jumps. Remaining jumps, I will sum that up and ask my bricks, bro, are you okay to solve this? Are you okay? Which means the remaining sum, is it less than or equal to your number of bricks? So if that is the case, you will see the complexity will be O of n log n square log n, right? Because you are going on to all the indexes one by one, and at every index you are just checking, bro, is it possible that I can reach here? Again, choosing greedily is this operation that you will grab out the maximum k jumps and give it to your ladder. Now, as you can simply see, you are doing a simple sorting and figuring out the what? Figuring out the maximum k jumps, right? So if for sure in a sorting, if you are figuring out maximum k or minimum k elements, then you know that you can improvise that by using a min heap or a max heap. So I know that n log k, I know that in my heap I can store only the k elements. Again, there will be a bit variation in this because I want to keep a summation of my smaller n minus k elements if I am at the nth index. But yes, still it will be roughly of saying that I will go and try for all the values up till the nth value, but my heap will store only top k values, remaining values I'll keep in my sum, all that stuff. But it can roughly be optimized because I want k max or k min elements, so it can be optimized to say that I can use a min heap or a max heap depending upon how you implement it. You can use both of them. You can use a min heap or a max heap, and by that you can optimize that complexity a little bit. But can you optimize it more? Yeah, you can, because if you just clearly see one fact, what is happening? You are going linearly. Okay, I went here, then 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 I went here, and then I went here, and then I went here, and then oh, I went here, it stopped. Which means if it stopped, then next onwards it will also keep on stopping. So it is kind of a pattern that okay, up till this index it is right, it is possible, and after this index it is not possible. This is the exact pattern of binary search. So rather than linearly going on to all the indexes, all the I indexes, I can just do a binary search on the index itself and can figure out the exact same greedy behavior and see if it is working or not. So earlier, rather than going on to all the indexes again and again, which was taking O of n time, I will now use a binary search and will go on and do a binary search on the entire length of n. Thus, I will be using a O of log n because I'm doing a binary search because of my pattern, which I can easily see that starting it will be possible, ending it will not be possible going forward, because for sure you will not be able to have those jumps considered for your bricks. And n log n will for sure be there because we have some greedy behavior going on here. Sorting, again, you can still optimize that taking the min heap operation, so that I'm not considering because still it is O of n log n square. This is O of n log n square. Now the interview will again ask you, can you again improvise it? Which means for sure either you can do it in O of n or you can do it in O of n log n. Now I'll use the exact same. Again, you have been seeing I have been using the greedy behavior so far. I have been using a greedy behavior so far. I mean, every time I have been using this greedy behavior. But I'm right now saying I was checking for this greedy behavior at every index, kind of, right? Because in this binary search, I was checking this greedy behavior at those log n places. In my linear search, I was checking this greedy behavior for those all the n indexes. Now I am saying, bro, what I can do is I don't need to check this greedy behavior every time. Only when I am in struggle, in emergency, I will go and check this behavior. Bro, what do you mean by that? I mean by that is, see, when is the emergency coming in? Emergency coming in, let's say you have some number of jumps which you have to do, but your ladder cannot perform those jumps, which means your ladder is 2. Your ladder is your ladder number, which means you have 2 ladders, but you have to perform 3 jumps. Oh, now's the emergency. So the third jump, it has to be performed because of my brick. So in that kind of emergency, only in this emergency, I will use my bricks. I don't know why balloons are flowing, but yeah, in that kind of emergency, I will flow my bricks. I will use my bricks. Now, in that case, oh, Aryan, which means but you will use your bricks. But you are also saying that if you are using your bricks, then you are using your bricks. But you are saying, but you earlier spoke that you will only use your bricks in case when the height or when the jump is very small. Yeah, bro, true. So if my size increase, which means, okay, ladder was 2, I have a 3, which means my size has increased. So that third jump, I will grab the minimum jump possible and I will use that third jump for my bricks. Let's see how. So I will keep on going, and in the emergency only I will use my bricks. Let's see how. So again, I am at the ith index. I will go and check for the i+1 to know the diff, jump diff. Okay, diff is 8. Okay, I will put in some data structure. Again, it is some data structure. Okay, I just put in value 8. But how to define that data structure depends upon what operation I will perform on next. Okay, one operation was pushing in this 8 value. Other operation will be, let's say emergency comes in. I told you what's the emergency. Emergency is your ladders are 2, but you have to perform a 3 jump, which means 3 diffs you have to resolve. So third one, you have to grab out the minimum diff and try to handle it with the help of your number of bricks. So I want some data structure which will give me the minimum diff, because it is a heap, it is a data structure which is getting in the values, which are diff values. So I want to grab the minimum diff as soon as possible. So either we can use a priority queue or we can use a multi-set. Priority queue is a min heap. Again, you can use a min heap and you can use a multi-set. Both can give you the minimum element in the smallest possible time, and that's how you define the data structure. So you can use any of them. Both are completely fine, because insertion in this data structure will also take a login time, and grabbing out the minimum element will also take a login time. Insertion in this will take a login time. Grabbing out minimum element will take a login time. So both of them will perform exactly same in this problem. Great, let's go on to next. Okay, I am at I'll check i+1. Oh, the diff is negative, which means I don't want to do any jumps. Cool. So nothing happens here. My data structure only contains 8 right now. Okay, I and i+1. Diff is actually 5. 7 minus 2. Oh, diff is 5. Okay, I can keep in my data structure. Again, the size of this is 2. So for sure, I know I can easily use my ladders for it. No emergency coming in, no worries. Then I and i+1, diff is negative, no worries, move on. Then I and i+1, oh, diff is 15, no worries, push that 15. Bro, it became size 3. And I have only 2 ladders. No worries, bro. Grab out the minimum diff element. Grab again, pushing that 15 diff. It has become a size of 3. Grab out the minimum diff element and then try to handle it with the number of bricks you have right now. Bricks, I had 10. I will handle this 5. I will remain with the 5 bricks. Okay, no worries, bro. Everything was handled. Everything is okay, completely fine. Simply go on. Okay, I am at i+1. Oh, diff is 2. Diff is 2. Okay, simply push that 2. Bro, again the size increased. No worries, bro. Calm down. Grab the minimum diff out. Handle it, try to handle it with the bricks remaining. Bricks remaining were 5. I will try to handle it. I will get bricks remaining as 3. Okay, so number of bricks remaining are still, which means bricks were still there to actually handle this case. No worries, bro. This is completely okay. Now move on. Okay, bro, I'll simply move on. I am at i+1. Negative. Oh, bro, nothing happened. Simply again move on. i+1. Diff is 16. Okay, simply push that 16. Now again try to grab the minimum element. Minimum is 8. Bro, minimum diff is 8. I want to require at least 3 bricks. Sorry, bro. This will not happen. So I cannot go from I to i+1. I cannot do, because ladders are not remaining. Bricks are not remaining. No matter what, I cannot do. Even in emergency, I cannot grab anything. So that's the reason it will simply stop here. So the answer is index 7. Again, remember, I want to return the index. Maximum index it can reach is 7. And that's how you can simply solve it. Cool. The code is exactly very short and simple. Firstly, you will get a priority queue that is a min heap. Again, you can also take a max heap. It's just that you will have to do a small modifications, which means max heap, you will try to push in the negative values so as to grab the most negative value out. So a small modification in the input like how you solve it, but still you can also use a max heap for the same case, but make sure that you handle with the negative sign properly. Now I took a standard min heap itself. This is a min heap which I made of integers. Now I'll simply go on from the I equal to 0 to I equal to height, size height minus 1, because I know if I'm at I, I'll compare the height with I plus 1, right? So I'll get the jump length whatsoever I have to take, which means I plus 1 minus height of I. Now if the jump length is positive, which means I have to do actually a upper jump I have to take, then actually it is a use case for me. If the jump length is negative, oh, that's a lower jump, nothing, you can simply go on and try something else. So if it's a jump length is positive, which means it's an upper jump, then if it's an upper jump, then simply push that in a priority queue, as I showed you in the dry run also. Now if you push this something in the priority queue, then you will check, bro, is it an emergency? Emergency will come in if the priority queue size will become more than the number of ladders which you have. If it is the case, it's an emergency. So if something is an emergency, simply grab out the minimum jump length, subtract it from the number of bricks, and simply you can simply pop out that specific number of that specific jump length. You can just simply pop out because it is used by number of bricks. But bro, you subtracted that, which means you considered the number of bricks will be more. Bro, I'll also check if my number of bricks have become negative, which means this index was the last index which you could have gone in, simply return this index. Else, if you go out of your this loop, which means, bro, you went on to all the indexes, so your final answer is n-1, which is the last index. And that's how, in this simple short code, you can simply solve this in O of n log key time, because your data structure only contained the k elements, and for sure the space is also O of k. And that's how you can simply solve it. Cool. That is the reason I discussed. Again, with this one, you would have solved it using your simple DP. Then we went on to greedy, the actual brute force greedy. Then we went on to a better approach of using the greedy. Then we went on to my binary search approach. Again, this binary search itself could have been optimized, and we could have reached n log n from this binary search itself. But then the most optimal approach is because of our min heap, and that's how you can simply solve it. Again, the video has gone to 27 minutes, but many people will just discuss this portion of the video, which will take only 5-10 minutes at max, because it's a simple min heap problem. Cool. Thank you for watching. Goodbye. Take care. Bye bye.